Dear all, welcome to another session of Architecture and Programming Models for GPUs and coprocessors. We're currently in part 3 of the lecture, and that part is called the graphics pipeline, and it's really the architecture part of the lecture. In the last session, we already saw what the graphics pipeline actually is. Like we saw that stacked diagram that I called the graphics pipeline, and that was really the rasterization algorithm, like the rasterization algorithm 2 that we learned about in the computer graphics part. And in this rather theoretical part of the lecture, we'll now talk about how a typical GPU architecture would implement the graphics pipeline based on the rasterization algorithm. So, and before I want to go into the details about GPU architectures, I want to spend a few words on scalability of those architectures. Like those considerations on the one hand will help us understand the major characteristics of GPU architectures, but they are also meant for us to understand major bottlenecks with typical implementations and with typical GPU architectures. So in the last session, we already had a discussion about traditional GPU architectures, and we learned that those architectures evolved and that they are basically focused on bulk processing of data. So the data that we usually process are vertices and fragments, and we usually have thousands and even more of them. And the compute workload that is applied to those data items is relatively homogeneous. So there's usually relatively few divergence in the execution flow, and we assume that the basic operations that are applied to the vertices and to the fragments are relatively the same. And that later even allowed us for the processor types that are used for the different, like for the vertices and for the fragments, that allowed those processor types to converge, so that we finally ended up with what was called a unified shader architecture. And those unified shader architectures are typically like a number of processors, and those number of processors again contain like a number of cores, and that adds up to the architecture consisting of really many cores. And those many cores, on the other hand, are relatively lightweight, so their clock frequency is relatively low, and the whole architecture is basically optimized for throughput. Like we have caches, and usually there are caches associated with each of those processors, and then the cores share the caches. But we have to make really sure that when we access the cache, that we do this in a very coherent fashion, because accesses to these caches are usually high latency, and so is the overall pipeline. That is, whenever we access memory items in the memory hierarchy, this usually incurs relatively high latency. And that means whenever we access memory, we should make sure that we access a lot of memory at once, and that the data accesses are relatively coherent. And all that is opposed to how CPUs usually work, where we have those high clock frequencies. On the other hand, only a moderate number of cores. And we have those complicated like branch prediction units, out of order execution units, and the whole design centered around huge caches. So just to give you an idea of the proportionality, on a CPU we usually have that huge cache hierarchy, and on the GPU we are dominated by multiple very lightweight compute units, and those compute units are really optimized for throughput. And this is like the big picture of what a GPU is. So the big picture is that we have a many-core architecture with many very lightweight cores. On the other hand, we have high latency, high bandwidth memory. But this is only part of the bigger picture, because what's really important about GPUs is that they are relatively heterogeneous architectures. Like we, on the one hand, have those programmable units, like those shader cores and shader processors. But on the other hand, we also have a number of fixed function units. And when we have a graphics program, then we have to route the data flow basically through all those fixed function units and through the programmable units. And that's what makes GPU architecture so complicated. The characteristics of the architecture per se, so that they are relatively parallel, that they consist of many cores, and that they are essentially like small vector processors, This is only one part of the bigger picture that describes what a GPU really is. But the other part really is that there's a bunch of different functional units, and those functional units are relatively heterogeneous. And at the same time, those functional units also share parts of the die. Like, for instance, it's not uncommon that you have an L2 cache, and that L2 cache is accessed by the shader processors and by the shader cores. And the frame buffer has also access to the L2 cache, or other fixed function units, like for instance raster engines, can access caches that are also accessed by, say, by a shader core. So this whole architecture is relatively heterogeneous, and on the other hand, GPUs usually are like coprocessor cards, so there's also an interplay with the host computer, and this is usually not a synchronized interface, like in a fashion where whenever we talk to the GPU, the execution blocks. But on the contrary, when we use a GPU, the communication with the GPU is usually highly asynchronous. So when a GPU vendor designs a GPU architecture that is based on the rasterization algorithm, then they have to make sure that the design scales along the whole pipeline. That is, there are like certain locations in that pipeline where we can see bottleneck, and those bottlenecks can potentially starve the whole pipeline. Like when we analyze the typical GPU architecture, then we, in the very beginning, have the user specify input data like vertices, and those vertices have a connectivity, and the vertices have normals associated with them and the colors. And those vertices, they are passed through the vertex phase of the algorithm and through primitive assembly, and then we eventually have triangles, and those triangles are passed through the raster engines and through the fragment processors, and that eventually will produce like pixels, and those pixels have passed the depth test and they were blended. And along those stages, like on the vertex stage, on the fragment stage, we usually use texture images, and quite often our GPU architecture has like maybe a dedicated region of memory for textures. And then finally, when we have shaded our pixels and all the pixels have passed the depth test, and we determine all the final pixel colors, we can really display them. And along that whole pipeline, everywhere where there's an error, basically there can occur bottlenecks. And if there are bottlenecks, then the architecture can become dominated by those bottlenecks, and the rest of the pipeline can starve. Like for instance, if the user supplies input data at a certain rate, but the GPU is not able to process the input data at that rate, like the handover between the input data from the user and the GPU isn't like fast enough, then this can become a bottleneck, and the whole rendering algorithm is limited by that bottleneck. And we then say that the algorithm is input data rate limited. Like on the other hand, if like the transform and clipping phase aren't fast enough and cannot produce triangles at a rate fast enough for the raster engines and for the fragment processors to operate at full throughput, then we say that the algorithm is limited by the triangle rate. Again, this is the typical limitation that we saw addressed with those uniform shader architectures. Like when we have a vertex phase where there's much more work to do than on the fragment phase, then we have this problem that the algorithm is limited by the triangle rate. And the solution to that for the vendors was to introduce what they call a uniform shader architecture. And when the fragment processors and the raster output units or raster output processors aren't able to produce new pixels at a rate fast enough, then the algorithm is limited by the pixel rate. And we can also be limited by the texture rate. So texture rate limitation on the one hand means that the accesses to the texture unit just aren't fast enough in our fragment processors or our vertex processors, depending on who accesses the texture, those units might starve. But texture rate limitation can also mean that the texture memory just isn't big enough to contain textures the size that we want to use. And then we maybe have to like consecutively bind several textures And that can also lead to scalability issues with texture accesses. Yeah, and then finally, when the interconnect or the functional unit that transfers pixel from the frame buffer to the actual display, like the physical display isn't fast enough, then we're limited by the display rate. And when a vendor designs a GPU architecture, then they have to make sure that none of those bottlenecks limits the overall architecture. And as you can see, along that whole pipeline, we have both programmable units, like on the vertex stage, we have programmable units, or here in this circle here, we have the fragment stage, and we have programmable units that are working on this stage. And on the other hand, we also have like fixed function units. Like, for instance, on the texture stage or on the display stage, we have fixed function units. And a typical GPU architecture, therefore, is a heterogeneous interplay of fixed function units and of programmable units that access the same types of data throughout the pipeline, and that need to do that in a way that no unit can become a bottleneck and thus cause the whole pipeline to starve and thus introduce load imbalances and bottlenecks. And consequently, what we just discussed define the key metrics when designing a GPU architecture. Like the input data rate is the rate at which commands can be issued to the GPU, and those commands include draw commands. They include commands that incur data movement, like where we issue geometry to the GPU. Another key metric is the triangle rate. That is the rate at which the input geometry can be transformed and clipped and then handed over to the raster engines, like typically in the form of edge equations. And another key metric for a GPU architecture at scale is the pixel rate. That is the rate at which those triangles can be processed, like how fast the raster engines operate, and then how fast the fragments can shade those fragments and retire them as pixels. So the texture rate is another key metric that on the one hand determines how fast we can access the texture units, but on the other hand, this also determines how many textures we can actually deposit in texture memory and what the size of those textures are. And then finally, when we have our pixels, and our pixels are like in the frame buffer and they are assigned colors, then the display bandwidth and the rate at which we can retire pixels to the display is also a key metric that determines the scalability of the GPU architecture. And we shall start our discussion of the graphics pipeline at the very beginning, that is, at the interface between the host CPU and the graphics device, so the GPU. And that interface consists of, on the host side, of the runtime and the driver, and on the device side, so on the GPU, there's a functional unit that is called the command processor. So when the application submits geometry and submits draw commands, then it does that by talking to the driver, and the driver talks to the GPU via the so-called interactive host interface, and the entity that is passed through that interface are so-called commands, and those commands are processed on the GPU side through the command processor. So we will now discuss the host interface in depth. And in order to understand the host interface, it is first important for us to gain a bit of understanding of how device-side drivers with typical OSs with monolithic kernels actually work. And this is the very first thing that we will have a look into. So when CPUs nowadays on the hardware level implement something that is called the protected mode. And the protected mode basically devotes different privileges to applications that run in either of a number of different modes. Like the operating system kernel, for instance, usually runs in a very highly privileged mode. And in this highly privileged mode, the operating system kernel can directly access devices that are connected to the CPU, for instance via PCI Express or via USB or via PCI. The kernel does that by so-called device drivers, and those device drivers are vendor-specific programs that model the interface between the devices and the kernel. Like the kernel accesses the devices via the device drivers, and then there are like user mode programs, and those user mode programs usually run in a less privileged mode. And the system here is usually designed around something that is called protective rings, like where we have the kernel run in the highly privileged ring, like in ring 0. And like on IBM compatible systems, for instance, there traditionally just is no ring 1 or 2 that any applications run in. And so the user mode applications, they run in ring 3, and ring 3 is actually has lower privileges than ring 0, where the kernel runs in. And that means when our user mode application wants to access a device, then the user mode application has to do so by negotiating that with the kernel. And that negotiation happens through a certain API, and that API consists of so-called system calls. So system calls basically are like functions, and those functions allow the user mode applications to negotiate with the kernel. So, and a typical system call might, for instance, be that we ask the kernel that it opens a file. Like we might use the library call fopen, and then the fopen library call would internally use the system call open, and the system call open would be issued to the kernel, and the kernel would then negotiate with the hard drive or with the SSD drive that is connected via an interface. And then the kernel would return something that's called a resource handle, and that resource handle would allow our user mode application to access the device. And then in the end, like the user mode application would release the resource through the resource handle, and by that issuing another system call, like the close system call that is exposed, for instance, through the fclose library function on Unix systems. And that way, the user mode would be able to access resources that the operating system kernel maintains, but without having to access addresses that are bound to a highly privileged mode. And that way, we basically protect operation of the operating system kernel. So whenever there's like a bug in our user mode program, or there's actually a vulnerability, we're relatively certain that this vulnerability won't spill into the operational mode of the operating system's kernel, which is pretty important. And as it is so important, this is actually a feature that is not only supported by the OSs, but actually by the hardware, like the protected mode that I just outlined. And here I exemplified that using IBM compatible CPUs is something that is implemented on the hardware level. And obviously, the protected mode is also something that our GPU device drivers have to fit into somehow. So we have our user mode applications running in a lower privileged mode, and then we have this basically what is an API that allows us to access the operating system. And that API is comprised of system calls in the one direction, that is in the direction from the user mode application to the kernel. And in return, the kernel will usually answer by providing the user mode application with resource handles. So this is how the handshake between a typical application on the CPU and between the operating system works. And like on IBM compatible systems, we have this protected mode where we have ring 0 and ring 3, and software like that is highly privileged, like device drivers and the kernel itself, they run in ring 0, and user mode programs, they run in ring 3. And the system call and resource handle paradigm is basically what can be thought of as an API that allows us to access the operating system. And it is important to note that whenever we use that API, that is when we call into the operating system, this is usually a relatively costly and time-intensive operation. So whenever we issue a system call, this usually takes like a lot of time. You don't want to do that in like a time-critical applications. And therefore, like you also want to reduce the number of system calls that you issue from your application. So here's just a very simple example of that, where I have this example C file here, and the C file really doesn't do very much other than calling a library function, and that library function is the fopen function, so the file open function. And the file open function returns a handle, like a resource handle, and then we could like I don't really use the resource handle here, but we could. And then in the end, I just release the resource handle. So in my application, basically using library calls, like calls to fopen and like calls to open network sockets or calls to generally talk to devices. And internally, like this translates to so-called system calls. And those system calls, like here's like some output that I generated via the strace tool that allows me to see which system calls are actually issued by library calls. Like this is actually easy enough to demonstrate. Like here I have this this file fopen, and the fopen file basically does what I showed earlier on the slide. And I compiled that into this this application fopen, and I can call the fopen application, and it doesn't really print or show anything. But when I run the fopen application with ltrace, so ltrace would just print all the library calls that I'm using. So the calls that are available in user mode to access system resources. I see that the application calls fopen and then calls fclose, which is expected because this is what we're doing. And when I like call strace on the application, then I can see all the system calls that are executed. Like for instance, I see the break system call that will expand the memory segment that the application uses. I can see mmap, which is also concerned with memory allocation, and I see other stuff that's happening that like presumably has to do with the linker trying to link in some functionality so that I can use those library calls. So and then in the end, I can see that the open and the close system calls are being called by the application. And what is relatively common today is that operating systems adopt so-called monolithic kernel models. That is, the operating system runs in protected mode, and the operating system allows for extensions via so-called kernel modules. And those kernel modules are basically programs that can be loaded or unloaded at runtime. Like for instance, Linux or BSD systems adopt that model. And then the vendors, they write device drivers, and those device drivers are usually realized as kernel modules. And those kernel modules have access to like external resources to devices because they run in high privilege mode. And like the driver in general, however, is then usually a program that consists of like a device driver part and a user mode part. Like it's pretty common that the driver, like in its entirety, consists of both device drivers that interface with the operating system and that are like kernel modules, and on the other hand that there are user mode parts, and those user mode parts run in unprivileged mode. And this is also usually how graphics drivers are realized. And we will now have a discussion of the host interface of the graphics card, and we'll base that discussion on the Windows display driver model, like which was introduced with Windows Vista, and that allows us to understand the various components and the interplay of the user and kernel mode display driver parts that are relevant. And from that, we will learn how a asynchronous host interface is realized based on this example. And the reason that I chose the Windows display driver model here is because the documentation is actually pretty good. Like in contrast to, for instance, the models that are adopted by other operating systems like Linux, the documentation is very good and will allow us to understand what the design decisions were actually. Like the Windows display driver model sees the IHV, like the independent hardware vendor, like NVIDIA or AMD, supply only very little part of what one would call like the driver or the runtime. Like Windows basically implements quite a lot of the display driver part. Like the larger part of that is actually integrated into the operating system, and the independent hardware vendors actually provide only parts of the interface. In particular, this is a user mode display driver part that is supplied by the IHV and a kernel mode display driver part. Here, notably, the parts that are not supplied by the IHVs are the runtime, like what you would see as like the libOpenGL, for instance, and that comes from the operating system actually. And what's also worth noting is actually that the GPU scheduler is provided by the operating system. So we'll learn a bit more about the operation flow there in a little bit, but suffice it to say that basically the command management is pretty much in the hands of the operating systems, while the actual driver parts that are supplied by the IHVs are like comparably little actually. Like for instance, the very way that commands are buffered on the driver side, for instance, come from the operating system and not actually like as one might assume from the hardware vendors. So like in general, the IHVs, they provide kernel and user mode device drivers, and the GPU scheduler with this model comes from the operating system. So and like there with the Windows display driver model, and also with other models that operate in a similar fashion, you usually have a share of responsibilities. Like for instance, in this model, you have the user mode part of the driver being responsible for patching and compiling shader programs, for compiling shader programs into an intermediate representation so that it can like later be compiled into machine language. And this is an interplay between the parts that are supplied by the vendor and between the runtime that comes from the operating system. So maybe I should say a few words about what I mean by patching here. So it's kind of an open secret that vendors like NVIDIA or AMD, they try when there are like certain applications, like certain games, for instance, then they're pretty interested in that those games or applications are fast, like for instance in benchmarks. And it's kind of like an open secret that there is a common practice for the vendors to very closely analyze those certain applications, and in particular the shaders that those certain applications use. And there's this general approach where the vendors, who like obviously have a certain knowledge about the hardware that the game developers or the application developers generally don't have, and the vendors like therefore commonly, especially like with major games, for instance, they like take the shader programs that were provided by the application developers, and like those shader programs obviously they at some point like end up in the command stream, so they're passed to the driver, and at some point the IHVs are like able to intercept those shader programs. And there's a common practice that the IHVs supply custom programs that do the very same thing, where they really make sure that the outcome of the shader program is the very same, that the output is the very same, but the shader programs are better optimized for the particular hardware. Like this is kind of like an open secret. Everyone knows that the vendors do that for major games. It's really like common practice, and like when you download a major driver update, then pretty much of that actually goes into patches that are application specific. And this is really common practice, and this is what I mean when I say patching here. Like this is what the user mode driver does here when I say patching. So the user mode drivers are responsible for compiling the shader programs into the intermediate representation, and the vendors are kind of free to intercept that stream of shader programs and do pretty much what they want with that stream. given, of course, that whatever they do, that it doesn't tamper with the actual output of these shader programs. And like what the vendors and the operating systems try to do is defer as many responsibilities as possible to the user mode part of the display driver. And this is mostly to do with security. Like every part of a program that runs in kernel mode potentially can bring down the whole graphics subsystem of the operating system. Like when there's a bug or a vulnerability in the kernel mode part of the driver, then this actually has the potential to freeze the whole graphics subsystem or even crash it. So there's a general tendency towards having most of the logic in user mode, and only those parts in kernel mode, like in privileged mode, that actually need those extra privileges. And what's most noteworthy about this type of display model, of this type of display driver model, is the fact that it supports multi-user, multi-process accesses. And that, of course, requires some type of virtualization layer on top of the actual graphics device driver. And in particular, the driver model ensures that no process can access graphics memory of other processes. So there's a dedicated virtualization layer that is concerned with paging and with address translation and similar matters, and that is part of the user mode display driver. And with that, we'll exemplarily have a look at the Windows display driver model. It's not important to learn that whole operation flow by rote. It's not necessary, but it's important to understand what the interplay here is. The driver or the display driver model mostly consists of 4 parts, like the runtime that comes from the operating system, the user mode display driver that comes from the vendor, the scheduling and kernel mode subsystem that comes from the operating system, and the kernel mode display driver that is supplied by the vendor. Again, you can already see obviously the application runs in user mode, and the interface for the application is the runtime. So the application uses a runtime, like for instance the OpenGL runtime or the DirectX Direct3D runtime, and then issues certain library calls. Like for instance, it tells the runtime that we want to create a device, like a device abstraction that allows us to query the properties of the actual hardware that's underlying. And then you can see the interplay here, like the user mode display driver and the runtime, they will negotiate with the kernel mode part of the display driver, and then will return context objects to the application. And when the application creates a resource, that will result in a resource allocation. And then you can see that the application issues draw calls, right? And the draw calls, they are issued to the user mode display driver part. And then in the end, when the application thinks that it should display the image, it sends a flush or present result, and that flush and present result is then dispatched to kernel mode. And in kernel mode, things happen that have to do with the command buffer, where we'll talk in more detail about in a little bit. And then that causes the display driver to eventually submit the command buffer and then send a notification, finally send a notification when an image was rendered. So we'll go real quick over the control flow of this model. This is an exemplary discussion. So, but it should be pretty much representative of how those models work. In the very beginning, the application initiates rendering by requesting a rendering device, and the runtime will then return a rendering context. And the rendering context is pretty much what we discussed when we talked about OpenGL and when we talked about state objects. It's an abstraction for the 3D rendering state that the application can interact with, and that the application can modify via certain calls depending on what your API allows you to do with it. And then at the same time, the user mode display driver, The vendor-supplied user mode part will issue with the kernel subsystem that we want to create a device, and then the user mode display driver will eventually return the context that was requested by the application. So when the application allocates resources, resources would typically be like vertex buffers, general array buffers, textures, frame buffer objects, all those things. Then the application tells the runtime that those resources are required and that we want to allocate them. And the runtime negotiates that with the user mode display driver, and the user mode display driver dispatches those allocations to kernel mode. Then the application, like we just saw, the application will perform rendering and therefore will issue draw commands, and that will finally tell the runtime that we want to present the image. So the image should be displayed, and that demand that we want to present an image is passed over to the user mode display driver, like the vendor supplied part of the user mode driver. And then the kernel mode subsystem will buffer all those calls that were supplied by the application and that were passed over from the user mode display driver, and it will do so in an object that is called the command buffer. There is a buffer that is associated with each context, and it will contain all the commands that the application passed to the kernel mode subsystem of the driver up to some point. And this command buffer is in a dedicated region of memory, in a privileged region of memory, because it's running in kernel mode. And the command buffer resides in a memory region where the GPU has access to via direct memory access. So the command buffer with the draw commands and the final present command and other commands that are potentially passed to the GPU, like state changes, etc. They reside in a privileged memory region, and the GPU can access that region via DMA. So in those command buffers, they are allocated to each application and to each context that the application potentially has. When the application runs multiple threads, then it potentially also has multiple contexts. So the user issued a bunch of draw commands, and while doing so, the driver buffered those commands. And then when the user finally issues a present command that we want to see an image, that of course doesn't happen instantaneously, because we already saw that the driver will, before anything really happens, before anything is any user commands are actually processed, it will just buffer them so that it can that the GPU can access the command buffer via DMA at some point where it makes sense for the GPU to do so. When the GPU actually is idle and as an available time slice to process the command buffer, and then it will usually also optimize for not copying individual commands, but it will wait until the command buffer is filled to some extent. So we, on the one hand, we have multiple command buffers per application per thread, but we still need to synchronize. But for instance, we need to synchronize when the application told the runtime that a image should be presented. As that doesn't happen instantaneously, we, on the other hand, don't want the application to block, right? And therefore, the application basically uses a trick by inserting into the command stream a token. Yeah, and I mean, the idea behind it is actually fairly simple. Imagine we have our application, and the application has some linear control flow. The application processes some work over time, like in a thread or in multiple threads. And then at the same time, we also have our GPU operation. The GPU operates and is concerned with certain work packages, with command buffers, maybe from other applications, or maybe even from our application, but from other threads. So, and those two, they work concurrently, right? Our application runs in a operating system process, and the GPU also does some work. And as it's a coprocessor, it's per se is something that runs in parallel to the CPU. So we have those two entities, our application on the one hand and the GPU on the other hand, that operate in parallel. So and our application might at some time decide that it wants to submit like certain commands. Like the application now uses the GPU, and that manifests in GPU commands, and we already saw that this like eventually manifests in a command buffer. And this command buffer is like passed through the, for instance, through the Windows display driver model, is passed to the GPU and is deposited there so that the GPU can like eventually process that command buffer. And what's important now is that the application and the GPU can still work concurrently, right? Like we neither want to interrupt the GPU control flow nor the control flow of the application. So like in general, this is still possible with what we with the model that we're currently using, right? Like the application just deposited that command buffer in the GPU's queue where it like stores those command buffers, however this is realized, and like per se the application can just operate as it did before, right? So what the application, however, also does is it deposits a token, and that token signifies that after the command buffer was processed, we want to present an image. That is like after this command buffer was processed, all the draw calls ran through, and we want to synchronize. Yeah, we want to see an image, and we basically want to synchronize. And what the application does is deposits a fence, like a token, and this is usually done using language constructs like fences or barriers, and it places that right behind the command buffer. Like the application will really just call a synchronization primitive, like it will say here is a fence. It will not like actually place a token there. This is what the driver does. So the driver will place a token there, and that allows both the application as well as the GPU to now concurrently work on whatever they do. Like the GPU will process the command packages from other processes, like from other applications that are rendering at the same time. And the application also has other work to do, like has a thread that is running, and that it will now wait for the image to be rendered, but it will not like idle while waiting, but it will do something useful while waiting. And both entities like can do that, like they can still process their work. Like when the GPU encounters the token, then it knows that the command buffer was processed, that the application deposited there, and it then will present the image. And then based on the token, it knows which application was responsible for the command buffer, and then it will present the application with an interrupt, and will tell the application that an image was rendered and that this image was associated with the context of the application, and then the application can handle that event. And this is what we basically call an asynchronous host interface or a parallel host interface. So this is a very powerful concept because it basically allows us to concurrently use the GPU from multiple processes. And like this general model that is prescribed by the Windows display driver model can also be found in a very similar fashion on other operating systems. So the basic idea is always that you have your driver component and your GPU, and you have your application, and those run concurrently, and they try to keep those operations as concurrent as possible. And then they enter like synchronization primitives, like really lightweight synchronization primitives into the command stream that allow the GPU to finally notify the application that an image was rendered. And those tokens are they're really lightweight. They'll basically, I mean, this is of course an implementation detail, but in order to implement that, you basically would have to be able to identify the application, like the context that the token belongs to, and maybe the command buffer that the token was associated with, like the last command buffer that was processed. So that whole process is actually pretty lightweight, and it allows the application and the GPU and the driver subsystem to work concurrently. And this is the basic principle behind an asynchronous host interface. So I mean, with the Windows display driver model, we still had this interplay between kernel mode and user mode. So with this model, it is actually the kernel mode display driver that encounters that token, like in the command stream, and then it will like signal the kernel mode display driver that the command buffer was executed, and the kernel mode display driver will pass that signal over to user mode, and then the application can be notified. So we go back to this slide here. What we can see is like the direction of the arrows is like a bit significant. Like when we have our application like create devices and request context objects, then we see like we see most of the control flow going from the application to the device, and we only see like the device or the GPU like return a context object and then return that interrupt or that notification when an image was rendered. Like the control flow can already be seen to be mostly top down and not bottom up here, right, in this diagram. And if you look closer, then you will find out that most of the things that are happening here, like up until here to where we allocate resources, those are things that are like typically don't happen so often. Like the application will typically create a device on startup, and then will be returned a context object, but it will usually only happen once per application run, or maybe once per thread that has access to the GPU. So this is something that is actually pretty seldom. And then we already see that all the other communication mostly goes like from the application down to the eventually to the GPU. And we see that the real only communication that goes back from the GPU to the application is this interrupt. And like, I mean, you can imagine like that an interrupt is something that is actually not very data intensive, right? Like an interrupt is basically a bit that is flipped somewhere, and the application like can eventually like maybe pull that bit or like however the hardware implements this. But the way of notification is like has basically zero data that is transferred. So the communication back from the GPU to the CPU is as lightweight as can be. Like it's really the minimal communication that's imaginable, and that signifies that this whole model is based on a communication pattern where the application talks to the GPU, but not vice versa. So the GPU will like in the end really only send pixels to the display adapter, and like then perform the bare minimum of communication, that is like flip a bit somewhere in the hardware that the application can like pull or check and find out that that an image was rendered. So and therefore like an important remark here is that GPUs are pretty much like the whole GPU execution model is pretty much a one-way street. Like this asynchronous model that I just demonstrated is very powerful in a way that it allows for concurrency between CPU and GPU, but all that falls apart as soon as we read back data from the GPU to the CPU. So when we, for instance, like want to render it into an off-screen buffer, like into a texture, and then download that rendered result from the GPU to the CPU, then things become expensive. Because in order to do so, the GPU actually has to like empty the whole command buffer, and at the same time the CPU is not allowed to send any new commands to the GPU. And then that of course causes the GPU pipeline to empty and the CPU idles. And then when the CPU starts rendering again, the GPU will idle for some time because there are no new draw commands from the CPU. So readbacks, they require the application to perform costly synchronization that actually causes the whole pipeline to be emptied and then to be refilled again. And therefore the GPU execution model, as I outlined it here, is highly flexible, highly effective, but it's pretty much a one-way street. So, I mean, I outlined that all that based on the Windows display driver model, and this is a very particular model with very specific rules about how commands are executed and how they are deposited in the command stream of the GPU. And it's actually pretty nice that this model is so thoroughly documented. That's very helpful. And we will find that most parts of the GPU pipeline aren't as thoroughly documented. Like as soon as we take those commands and pass them over to the GPU, we will find that that there's very little documentation out there. The documentation is rather old, and we have pretty much a guessing to do, like in order to figure out what possible models could be implemented by the GPU. Like there are certain things that are known, but they are usually not specific to particular implementations. but they're more like theoretical models how things can be implemented, because the vendors really just don't tell how things are implemented. So, and the nice thing is that on the host side, we have a fairly good understanding of what's happening. This is also mostly due to the fact that the operating systems have taken the host side over to some extent. Like the part that the IHV supplies is actually very little. Like the whole scheduling and the whole command buffer handling is performed by the operating system, and therefore it's well documented and it's easy for us to comprehend. So nevertheless, the Windows Display Driver model is a very particular model, and we of course don't have to like rote learn all what's happening in that model, but there are like a few major takeaways. So one of the major takeaways is that the operating system implements this asynchronous model, and that asynchronous model supports multi-process operation in a very efficient fashion. Like the synchronization is really very little that's necessary, and the GPU and the applications can pretty much operate in parallel. And the model is pretty much dominated by the operating systems. So the operating system pretty much defines what the operation flow is with this type of model. The model is based on command buffers, and the command buffer scheduling is implemented by the operating system, so by the driver part that comes from the operating system. And synchronization inside that model is done using those very lightweight tokens that act as fences and that allow the GPU like to notify the CPU that some work was performed or that a certain command buffer was processed. And we will later also learn that there are other uses for fences than just for the GPU to notify the application that an image was rendered. But in general, the synchronization in the host interface happens through those lightweight tokens. So when we use fences as a GPU primitive, like a primitive that is supplied by the API, then the runtime and the driver will insert those tokens into the command stream, and the tokens will be processed in the way that I described it, and that this is the way that the driver implements synchronization inside the host interface. Another takeaway is that the command buffers, we will later learn more about the communication between the GPU and the host in regard to the command buffers. But it's important to note that the command buffers, they reside in a privileged memory region, like in kernel mode, like in a memory region that is managed by the kernel, and that the GPU can access this memory region via DMA. Yeah, and in general, an important takeaway about the host interface is that generally the graphics card is a shared resource, and that whole model is there in order to support multi-process access to the GPU. So, and on the other side, so to say, of this whole process is what is called the command processor. And the command processor is the entity on the GPU side that takes over the commands and processes them and distributes them to the functional units that are responsible for then operating on those commands. So, and we're now switching with our discussion from basically from the host side to the device side, and you will also find that things get a little bit fuzzy now. Because, as I said, the documentation is like rather scarce when it comes to what's happening on the device. And also because everything that is written about what happens on the device actually comes from so-called like great literature, like white papers that are published by the vendors, documentation and website by the vendors. So the literature on this, like the official literature when it comes to books and to papers, is actually pretty scarce because there are many implementation details here. And anyway, when you skim through the white papers, you here and there find like a lot of pointers of what's going on, and sometimes they refer to older architectures, like to architectures where it might indicate that this isn't the exact way that things work today, but how things can work on a conceptual level. Again, when we perform that switch, like from the host side to the GPU side, we have on the one hand we have the driver. And we have on the driver side, we have the kernel mode device driver, like this part of the device driver that is provided by the IHV and that runs in privileged mode, and that has access to memory regions that have higher privileges. And on the other side, like on the GPU side, we have the command processor. So the kernel mode display driver and the command processor basically are the pair of functional units on the host and on the GPU that interact in order to pass commands from the host to the GPU. And the command processor is just basically concerned with retrieving the command stream from the command buffer, and then the command processor pre-analyzes the commands, like only in order so that it can determine to which functional units it will pass the commands. Like typical example being, like the command processor might analyze if the commands are 2D rendering commands or 3D rendering commands. It's pretty common that the devices actually have like different functional units for processing either 2D or 3D rendering commands, and we'll place very little focus in this lecture on 2D rendering, but often they are just like go through a different pipeline, and the command processor might pre-analyze that, and this is basically it. So from there on, the command processor will really only reroute the commands to the functional units that are responsible for processing them. And the command processor implements either of two models, either the push model or the pull model. And with the pull model generally being more popular and the model that presumably is implemented on the GPUs nowadays. Like the command processor has so-called DMA engines, and those DMA engines, they can access that privileged host memory that we talked about, that the kernel mode display device driver manages, and where the command buffer is placed so that the GPU can directly access it. And the command processor has so-called DMA engines, and those can perform those DMA accesses. So, and in the push model, there's actually no DMA that is used, but rather than that, the host will actually initiate the data transfer, like through one of the transfer queues of the GPU, and then the synchronization happens by so-called register writes, where the host basically has access to certain registers on the GPU. Like the GPU has certain registers that contain flags, and those flags will tell the GPU if new data has arrived. And in the push model, the CPU completely initiates that. And in the pull model, I mean, the execution mode is one where the command processor actively requests if new command buffers are available, and then just transfers them via DMA. So GPUs usually support both models, like usually for legacy reasons, and they also allow for switching between the two modes. But generally, like the mode that is preferred nowadays is the DMA mode. Like DMA has several advantages. Like in particular, DMA helps with virtual address resolution that is just not necessary with DMA when we have a pull model. And it also helps because DMA binds relatively few resources on the GPU, which is of course also very helpful. So the GPU doesn't as those dedicated DMA engines, and other than that, it requires very few resources to perform the DMA transfers. So a few words about scalability. Like we already said that readbacks are exceptionally expensive because they basically cause the whole pipeline to stall and to run empty and then needing to be refilled again. And like generally, the behavior of the pipeline pretty much determines what we're limited by. Like when we have applications where the command buffer tends to run empty, like the CPU isn't fast enough at providing the GPU with new commands. We can see that by observing that the command buffers tend to be empty all the time. And this is an indication that our application obviously is CPU limited. And on the other hand, like if the command buffer is notoriously full, then we also know that the application is GPU limited, and the GPU is just not fast enough processing those commands from the command buffer. So, and a very typical design of a command buffer would be the following. Like this is based on a over 10 years old document by AMD, and this is basically a ring buffer implementation. And the ring buffer implementation sees the host maintaining two pointers, the pointers to the end of the ring buffer and to the start of the ring buffer. And the host will just fill the ring buffer, like which resides in DMA memory, in privileged mode memory. It will just fill the DMA buffer and will update those pointers. And whenever the pointer is updated, like it will through the so-called bus mastering write, like a write directly to a register on the GPU, will update those pointers. So, and the command processor on the GPU side will basically chase those pointers, like it retrieves the pointers from the read and write pointer registers, and will iterate based on those pointers and will retrieve new commands from the command buffer until the two pointers are the same. And that would basically end like when the start and the end of the ring buffer are the same. Then we know that the ring buffer is empty, and therefore there are no new commands. And this is like a very typical execution model where the host CPU fills the ring buffer and maintains those pointers and informs the GPU about changes to the pointers when new data has arrived. And the GPU, on the other hand, just chases those pointers. And then the question is really who's faster? Like, is the CPU faster at updating the pointer to the new data, or is the command processor faster at chasing the two pointers until they are same and the command buffer is empty? And this is a bit of documentation that we can actually find out there. And this is one way to implement this type of communication between like the kernel mode display driver and the command processor. Like the communication here goes through registers on both the host and on the CPU, and the CPU is able to directly update those GPU registers, and those accesses, they are so-called bus mastering writes. And those models are often hybrid. Like quite often the GPU would just use, like for instance, a ring buffer for typical draw or state change commands, and then would have like separate DMA buffers like for large data transfers. Like in a design like that, you would usually not have like vertex buffers floating around in the command buffer, or pointers to vertex buffers. Like that would basically stall the pipeline. And rather than that, those commands would be rather lightweight. And the GPUs usually provide like a fast lane for DMA transfer of buffers, like for instance vertex or array buffers. Yeah, the mode of execution I already outlined. Like the host would basically manage the ring buffer and manages pointers to the begin and to the end of the ring buffer, and then just writes new command packets into the memory regions. And of course has to make sure that the ring buffer won't spill over. Like when the host can't fit any new packets into the ring buffer, that means we're GPU limited, and then the host has to ensure that there's no new data written into the ring buffer. And then it will directly update the pointers on the GPU through bus mastering writes. And the command processor on the other side like accesses the ring buffer via DMA and reads the pointer address register, and then retrieves command packets until the queue is empty. Like that would just mean that the read pointer equals the write pointer. So we talked a lot about commands and command packets, and what those command packets actually look like is pretty much an implementation detail. But just to give you an example of what a typical command packet would look like. Like usually a command packet, like for this particular architecture here, a command packet would be like a 32-bit header, and then that followed by like a data body, and that data body would like be like n 32-bit keywords. Like for this particular architecture, for instance, there are like a bunch of commands, like ones that would, like for instance, draw a polyline, or initiate a memory synchronization, or that instruct the driver to and the command processor to load an index buffer. So we would on the one hand have those opcodes, like, and the opcodes would be stored in the header and would be like represented with like 32 bits, or with whatever bits the opcode is represented inside the header. And then that would be followed like by some data. And the data could, for instance, be like in a certain number of rectangles that would be represented using those 32-bit dwords, and then we would just have n of them, like so that we can fit the rectangles in. So this is, of course, very specific to certain architectures, But just to give you an idea of what those commands usually would look like, they would be kind of similar to what instructions are, but they also carry data along. So in general, like there are just different types of commands, like 2D draw commands or 3D draw commands, state changing commands, like when we want to change the color of a light source or the intensity of a light source. But also shader instructions, for instance, would manifest as commands. Like when we execute a shader on the GPU, like the GPU would be responsible for scheduling the shader at the time that the shader needs to be executed. But the shader instructions would actually manifest as commands, as some header indicating that this is a shader, and then the commands just being like a bunch of 32-bit integers, basically with the instructions of the shader. So and synchronization also would manifest as commands, like the token that we talked about earlier, for instance, would just be a dedicated command, like pretty lightweight probably, but still a command and would just indicate that this is a synchronization primitive. So earlier we had this discussion about OpenGL contexts and how they are abstractions for the GPU state, and we already talked about that those contexts are like pretty heavyweight objects. And I now want to devote a bit of a discussion on about how state changes, so changes to the context, would actually be implemented. Like we already discussed that from the host perspective, things are quite complicated, like because you have multiple applications and you have multiple processes and threads that have their own context. But things are actually even quite complicated when you only have a single application and an architecture like a GPU that is massively parallel. Like on a serial architecture, in this case, things are pretty simple. Like you would have your global state, and then you would use that state, and then at some point you would modify the state, and then you would use it again, and this would be perfectly fine because you only have one thread. But if you have like a bunch of threads, like a multi-core architecture, for example, then things are more difficult. Like in this very case, we, for instance, like if this function here would be executed by multiple threads at once, then we would get race conditions, right? So on a multi-core architecture, a possible way to overcome this problem would just be to use like a critical section. Like we would still have our global state, and the global state could now be accessed by all the threads. Like, and then whenever the state is modified, we make sure that we like enter a critical section and apply certain means that allow us to synchronize the access to the state, like whatever those are, like usually critical sections, mutexes, semaphores, and the like, and those allow us to modify the state, and of course they would serialize the execution. But this would probably not be so bad when we have like a 4 or 8 or like a bunch of threads. But the problem here is really that this type of execution model usually doesn't scale to like hundreds or even thousands of individual threads or cores that execute like GPU commands and then access a shared state. And this is obviously like a major challenge when it comes to GPU design, to make sure that changes and modifications to a single shared state are efficient, that they don't affect the whole pipeline. And of course, things are very fuzzy here, and the documentation is actually pretty bad. But here are a few thoughts. Like consider them to be like educated guesses, and also a bit based on discussion with people who might have an idea how things work. And like here are a few ideas how this could actually be implemented. Like in the very simplest way, we would have one global state like before, and the state would be shared. And then when we change the state, we would do that in a retained fashion. Like the GPU would just wait until all the commands are executed that use the state in its current form, and then would stall the pipeline basically. So would make sure that no new commands enter the pipeline. So when the pipeline is empty, the GPU would update the state, and then it would allow new commands to enter the pipeline. And that is of course pretty problematic because the pipeline stalls. And it's quite obvious that on an architecture like a GPU, which is streamlined and massively parallel, we really don't want to have pipeline stalls. So there is an alternative, and the alternative would be to basically have the state being a command. Like, we haven't talked much about how commands are processed by the GPU, but suffice it to say that commands basically can be imagined as floating through the graphics pipeline. Like, we have the graphics pipeline, and the commands are somewhere there in the pipeline, and they float through it and then are like executed in a pipelined fashion. And by having the state being a command, things are pretty flexible actually. Like, we would have a certain state, and the state would be a command, and all the other draw commands that access that state would just access that state command. And the state would usually be nearby, which is very helpful. And that way, when you have state changes, we don't like change a global object, but instead we just create a new command with the complete updated state. And then we just enter that state command into the pipeline, and then have all the other commands that are now affected by the state access like the command that contains the state. And this is, of course, a very flexible design. The obvious problem here is this obviously only works when the state is a very compact object. Like, when we have a very heavyweight state, and we learned that at least with the older APIs and the older paradims like OpenGL, the state is a very heavyweight, so pretty large object, and that of course makes things problematic because we have to copy the object all the time, and we also have to move it through the pipeline. So this is very flexible, but also has certain issues. And then there's a third alternative, and the third alternative basically would be the same as the retained mode of updating the shared state, with the exception that we don't have only one global object, but we have multiple copies of them, like a handful of copies of them. And this would mitigate the issue of the pipeline stalls a bit. Like, when there's a state change, then we would actually only update one copy, and we would only stall that part of the pipeline that is affected by that copy. And the commands that are affected by the other copies, they could just continue operation. So, and with that, we still have pipeline stalls, but we would mitigate them in comparison to the pipeline stalls from only having a single state object and updating that in a retained fashion. So those are just alternatives, and it's not really documented what the IHVs really do, but those are possible solutions to this generally quite complex problem. So we talked a lot about buffers and about concrete implementations, and one remark is in order is that, like, we have on the one hand, we have those command buffers and command queues that are maintained by the host and maintained by the driver. And then on the other hand, we have like certain APIs, like in particular Vulkan or OpenCL, which provide us access to those queues, where we actually have like C++ or C objects that appear as if we could directly access those queues. This is like those APIs. They are like actually very close to the hardware, but it is important to note that they usually don't directly map to queues. So there's usually not a direct mapping between a certain queue, like it is provided by the hardware and by the driver. But usually the queues are still like abstractions. Nevertheless, those APIs are usually quite near to what the hardware and to what the drivers do. Like, usually, for instance, a Vulkan program will allow you to generate dedicated queues, like for instance, in order to issue compute commands, and other queues to issue graphics commands, and queues to issue copy commands. So this is actually pretty close to how the hardware behaves, but generally there's not a direct mapping. Like, for instance, like, it's conceivable that we create a copy queue with Vulkan, let's take this as an example, and then under the hood, the copy actually goes through a ring buffer or a command queue. So there are just no guarantees that there is a direct mapping. Nevertheless, like, when we have those designs, like GPU designs, we usually see that reflected. Like, usually it is a property of the hardware how many ports there are to access certain queues. Like on this particular AMD architecture here, for instance, there are ports to access like 8 real command queues, and then there's like 2 dedicated DMA ports that allow us to directly transfer data without accessing any compute cores. And you can also see from this architecture here that there are those dedicated DMA ports, And those DMA ports, they directly talk to the memory controller. Like this would manifest as something that's called a copy queue in Vulkan or in like OpenCL. And the copies would then directly go through the memory controller and from there into DDR memory, and would not occupy any compute resources like any shader cores or something like this. So nevertheless, so apart from what the hardware and from what the drivers do, the software abstractions usually don't map directly to specific hardware. So when we, for instance, ask the device how many compute queues there are, that doesn't necessarily mean that this is the exact same number of compute queues that the command processor has access to. So we will, in our next session, start a discussion of the graphics pipeline, and we will discuss how the graphics pipeline is implemented on a GPU. And so we now talked about the host interface, so we're about to enter the graphics pipeline, basically. So we have our commands, and those commands are now about to enter the graphics pipeline. So an important thing to note here is something that is called API order, and I teased that already when we talked about the rasterization algorithm and about the blend operation. And for the GPU architecture, it is important. It's an important property that when we issue draw commands, like on the host through our graphics API through OpenGL, then the APIs, they guarantee a certain execution order of the draw calls. That is the same order in which we issued the draw calls. This is also the same order in which final pixels are retired. So it appears that the draw calls are executed in the very same order that we issued them. Like, this is not what happens in reality. Like, the architecture is massively parallel, and there's basically nothing happening in an order that a user specified, other than in the very end, when the pixels are retired by the raster output units. Then there is a guarantee that the order of the pixels reflects the order in which the triangles were specified. This is important because it pretty much influences how graphics cards are designed. This is, of course, a major challenge because we have basically a data dependency that reaches from the beginning to the end, right? And we'll learn about the flow of execution through the graphics pipeline based on the commands that were specified through the host interface, and with this restriction that there is a data dependency from the beginning to the end, and that is imposed by the API order. And in the next session, we'll start talking about how this is actually implemented on the GPU side.